Tuesday.
Good afternoon and welcome to the first of this series of UWEE Colloquium talks. So throughout this quarter, we're going to have both experts from outside, from academia, from industry, and also government, once government gets back to work, hopefully. And the other part of that is to introduce our new faculty, as well as to talk about research going on in our department and build a community across our department and across campus. For UWEE, it's a very exciting time, especially in areas related to computer engineering, research in computer engineering, and especially systems which work with large amounts of data. And these data could come from computing, from algorithms, from sensing, from measurement, and from more standard big data, which is how people look at big data problems right now. We call this whole thing big physical data, so it's looking at all kinds of inputs which are coming into systems. And we made 3 hires this year, very top-class hires. All 3 are related in some way to this thrust of computer engineering and big physical data. And one of the hires and today's speaker, Visvesh, Sathe, is definitely an expert in this area. His background, he's an expert in low power and energy efficient computing. Now this community does tend to use energy and power differently, so I'm sure we'll hear one or the other word from Visvesh about energy versus power. His background, he has a very strong pedigree. He has an undergraduate degree from Indian Institute of Technology, Bombay, as well as a PhD degree from Michigan, where he also got the Best EECS Thesis Award and was nominated for the Best Graduate School Thesis Award as well. He then went on to AMD, where he was a member of the technical staff and was part of the advanced technology group there, working on several aspects of optimizing microprocessor design. He has several papers already, many patents, and then we managed to get him here for joining us in this fall. Visvesh is a very serious researcher, but I did ask him for some fun facts I could share with you before we started. And he told me that his colleagues at Michigan have put together a file which he hopes will never make its way here. So I don't have access to that file. I don't know what he did in Michigan. But I did get a few facts, and here are a few. Some of you may relate to these facts. He has managed to lose all 3 of his diplomas, his bachelor's degree, his master's degree, and his PhD. So we just have to take his word that he has all these facts. He also claims that he got an F in a course because he forgot to drop the course in time. And we take his word for that as well. And finally, he put his advisor through the misery of 17 rewrites of the first paper he did. Now, he did explain to me that part of it was caused by an automated spell checker, where he had a paragraph where he talked about how provably correct his method was, but by the time it reached his advisor, it became probably correct. His advisor obviously was very concerned about it. So I'm sure everything he's talking about today is both provably and probably correct. So with that, I'll hand you over to Visvesh.
Thanks for the introduction, Vikram. Hi everyone, thanks for making the time to attend this talk. And for many of you, choosing me to be one of the 6 talks to attend. Before I go into this presentation about energy efficient VLSI systems, I'd like to take a couple of slides just to motivate the talk and just examine some of the systems that are power and energy constrained even today and going into the future. So we'll start at the near end of this power and performance plot here with ultra low power systems. These systems tend to be more energy constrained, such that the energy dissipation that they go through tends to limit their battery life as opposed to any thermal issues. One example of this would be a body area network. So you've got multiple sensors here that are each capable of energy efficient wireless communication to a hub that then translates this, that then translates this information over the network potentially to your healthcare provider. Essentially means to provide more scalable and continuous patient monitoring as one example. Now, higher up on the dissipation scale, you've got mobile applications. Your typical smartphone today has as many as 8 cores. And we're just counting the application cores, not even just the integrated graphics GPU. Now, these things not only dissipate as much as 2 watts, but what's particularly remarkable here is the wide dynamic range of power that they're now capable of dissipating in response to performance requirements. You're looking at a 10x range now. On your laptops, it's not uncommon to have your quad-core processor, driving along at 2 to 3 gigahertz with a thermal design power budget of 20 to 40 watts. Now, for both these applications, it's the power dissipation that tends to limit peak performance, and the energy dissipation also affects feasibility from the perspective of battery life. And I'll get more into energy versus power in a bit. Now, higher up in the dissipation scale, in the kilowatt range you've got enterprise servers. Now, these are typically used in banking and business analytics. They dissipate about 5 to 10 kilowatts of power. And even here, the number of cores that you can fit into one of these enclosures, as well as the speed at which these things can run, is also limited by thermal considerations and power delivery considerations. And you go all the way up to the megawatt range, and you consider supercomputers. So at 17 petaflops, Titan was, until recently, the most powerful supercomputer in the world. And it had 18,000 GPUs, 300,000 Opteron cores. And even for this supercomputer, the number of cores and the operating frequency of these things, and therefore the peak performance that you could get out of this supercomputer, was limited by your ability to actually power all those cores and the heat that was coming out of these things. All these applications are power and energy limited even today. So power-driven thermal constraints, of course, limit peak performance all the way from supercomputers down to mobile applications, especially where the appetite for enhanced mobile computing has made things like skin temperature increasingly relevant when we design portable parts. Energy dissipation continues to influence battery life in portable and mobile applications, but its impact on server economics has become increasingly prominent in the last 10 years, where now a lot of these server companies actually talk about the significance of wall power cost and the need for sort of performance per dollar in power, performance per watt per dollar sometimes. And that sort of come into the play as well. Now, we have traditionally seen roughly a 10x performance improvement every 5 years or so for the past couple of decades. And this has led to this explosion in data that we not only expect to store, but expect to retrieve and index at a moment's notice. Many scientific fields also have become increasingly reliant on computation to sort of drive progress in their fields through modeling and simulation. Examples of this are weather prediction, fluid dynamics, even new areas in computational chemistry. Now, all these benefits haven't just come from high performance. All these advances we've made have enabled low power electronics to become increasingly feasible for a lot newer applications. And sustaining this kind of growth in the future will mean continued improvement in performance, which, incidentally, is power and energy constraint. So now we think about designing efficient systems, not energy efficient, just good systems. Almost as a rule, you're going to be constrained by something, because by definition, you sort of hit the optimum when you're at the boundary of your constraints, aren't you? So from that perspective, it's not that big a deal that you're energy or power constrained. You're going to be constrained by something. So why this issue? The problem is that this constraint is beginning to swamp out all other constraints, and we don't have a recipe to date to try to address this issue in the future. And that's why it's become a huge problem that needs sort of to be addressed. Now, the reason why this problem has come and swamped us up is because traditional scaling, or Dennard scaling as it was known, has pretty much just come to a stop. The traditional sort of constant field scaling model, where every 36 years you could shrink your device, every 36 months, you could shrink your device, get a smaller, less parasitic, and therefore faster, and more energy efficient device sort of has run its course. It used to be you could scale your channel length in half every 36 months. In doing so, through constant field scaling, you'd get a 2x bump in frequency, all the while you are scaling your supply voltage down in half. And that sort of works out to a power reduction of a factor of 4. Now, more recently, however, we've seen short channel effects really raise their head. Back-end wiring interconnect challenges sort of become very significant. Now, the story is more like you scale your channel length in half every 36 months. You hardly get any improvement. Oops, sorry. You hardly get any improvement in performance. This 2F is pretty much optimistic here. All this while, you're not even scaling your supply voltage. You're barely making by just sticking to the same voltage, and you're not seeing any improvement in power. And on the other hand, you want all this performance improvement. You're not able to reduce power a teensy bit. So now really the challenge is on the side of algorithms, software, architecture, circuit, and system techniques. To address this problem, we can no longer constantly just rely on the process guys to keep delivering better devices to us as they have probably the better part of 3 decades, and then just enjoy the whole ride. We've actually now got to start working for a living. So the rest of this talk is outlined as follows. I'll take a quick primer on power dissipation, just to sort of get everyone on an even keel. And I'll also do an overview of energy efficient design techniques that are in use today. In the interest of time, I sort of dropped the idea of covering a whole bunch of different problems I might have had the chance to work on in the past few years. Instead, I've taken a vertical approach. So I'll only talk about one aspect of energy efficient design, which is resonant design. And I'll share sort of the journey that it took from being a purely academic idea into one that made it into a production microprocessor. And I was fortunate to be part of this transition. And I think it's an interesting story to sort of tell. So that's what I'll cover. And then depending on time constraints, I'll look ahead and discuss some of the challenges and opportunities that lie for energy efficient computing in the future. So power dissipation, right? Loosely breaks into dynamic power and leakage power dissipation. Your dynamic power is the sum total of all the resistive losses in your circuit due to toggling logic states. Now, it can be shown that the total energy dissipation that comes up due to dynamic switching can be shown as the sum total of SCV squared terms on each node of your circuit, where S is the probability that your node will switch. So if it's unlikely to switch, you won't dissipate as much power over time. The capacitance, C, that's being toggled. Obviously, a larger load requires more work. And the voltage, V, sort of the transition, the work, sort of the energy you're having to put into the system to get it raised up to a certain voltage and back down. Now, this energy dissipation is what drives wall power cost, battery life considerations, and we talk of energy efficient design in that sense. Now, power dissipation, on the other hand, is the rate at which this energy is being dissipated. So over a cycle, we're basically looking at the energy divided by a time period, or equivalently, just tacking on that multiplicative term F here, and we get SCV square F. And this is really what drives thermal constraints, such as the skin temperature on your cell phone when you're playing these very aggressive video games on them, or just the thermal limits that you have to consider when you're building your next most powerful server. Leakage power, on the other hand, also comes in several flavors. You've got junction leakage, gate leakage. But the one that's particularly relevant from a design perspective, which is another way of saying it's something we can actually do about, something we can do something about in design, is subthreshold leakage. So I'll just focus on that for now. Loosely speaking, it can be shown to be exponential in its dependence on VDD and threshold, sort of that blocked off region pretty much evaluates to 1, unless you're talking about sub-threshold circuits, which are interesting in their own right. But I'll sort of just leave that out for now. And here, the remaining sort of expression you want to keep in mind is you've got an exponential dependence on supply voltage for your leakage, and you've got an exponential dependence on the threshold voltage of your devices. On to some energy efficient design techniques. Now, this field has been active for well over a decade now. There's a number of low power and low energy techniques that have been in use. And nearly all of them, in fact, certainly all the ones shown here, reduce power or energy by addressing one or more of the terms that are in this power and energy, power expression showed here. So at the outset, though, one thing that really deserves mention is that digital design is, like a digital system, for example, is not some homogeneous blob of gates that you sort of synthesize in Verilog, get the whole thing done, and pass DRC, LVS, and you're done. Digital systems, for reasons of manageability and for function, have got a lot of structure and correlation. And designers exploit this correlation to achieve those efficiencies. So for example, if you look at the SoC example on the right here, you've got a couple of cores, some caches, a North Bridge, graphics processors, some accelerators in your SoC. Now, each of these modules have different computational latency, different throughput requirements, different durations of times they might even be active. Now, designers exploit this structure and try to achieve that low power by a number of techniques, some of which are highlighted in blue here. That's where structure becomes really important. For example, with the case of power gating, your GPU might be inactive for long durations of time, and it might make sense for you to power gate a few tiles or the whole thing for extended periods, isolating that GPU from the supply, and therefore cutting down on your leakage. Other ways to cut power are, for example, to use high VT devices in your circuits to reduce the probability that nets will switch through clock gating or signal coding, or to reduce the switching capacitance by logic downsizing. Now, all these techniques, obviously, come with trade-offs. So you've got high VT devices, that's extra cost on your fabrication process. Power gating and signal encoding come with a reduction in performance. And clock gating and logic downsizing have a cost in terms of PVT susceptibility. That brings us to probably a favorite among designers, which is to reduce the supply voltage. Because not only does that give you quadratic savings in energy and almost cubic savings in power, but also exponential reduction in leakage, remember. Unfortunately, that also is going to come with an obvious performance trade-off. In fact, we are talking about these trade-offs, and one of the most significant things to note are we haven't considered sort of the broad impact of runtime variation, supply noise, variability, aging. All these things start requiring margins on top of margin on what you've already designed. In fact, it might be a surprise to some of you to learn that the problem of voltage margin reduction in high-performance systems is a more urgent one than being able to voltage scale. Because we've been able to do that to a good extent already, but we've got so much margin on our parts that we're just dissipating all this extra headroom, and just the problem of figuring out how to intelligently assign it and modulate it at runtime itself saves you tons of power. The important thing to sort of remember as a key takeaway really is that you've got to understand your system. You can't see it in isolation from all the other blocks that exist. So I'll give you an example. At the outset, it probably sounds like a brilliant idea. Take each of those modules there that are in the SoC. Different colors correspond to different voltages. Give each of them their own voltage island. Tweak that voltage island just so that you meet the performance requirements for each of these islands. And now you're sort of running them at their most efficient state. Great. The problem is, how are you going to supply all these voltage islands, right? You've got two options. You'll do on-chip regulators, a separate can of worms I won't even go into right now. Or you sort of route all these power planes over to your chip, increasing the impedance of any one of these power planes, and therefore requiring a higher voltage margin due to supply noise. It is entirely conceivable that this really neat idea ends up hurting you more than it benefits you. So it's the thing to sort of really keep in mind is you've got to have the whole system in mind, and you have to understand all the different interactions that are sort of playing together in determining system power. On to resonant design. Now, in order to sort of understand resonant design, it's probably easiest to consider an analogy for how conventional switching works, and we'll go from there to resonant type switching. The physical equivalent of having an inverter charge and discharge your capacitive load is sort of like taking this mass or this load, charging it up involves sort of dragging it up this hill where you're investing energy into the system to raise its potential energy, bring it to the top, and now watch what happens when you discharge. You fling it down, the potential energy dissipates as heat, and you jump down, and you're ready for the next lift. Seems a bit pointless, but that's really what's going on. Resonant design asks the question, well, what if I had a spring? I'll hook it up to the ceiling, tied to my mass. I let it go. The potential energy in the spring translates to potential energy on the mass, sort of lifts it all the way up. But now, on the way down, that energy goes back into my spring. I don't lose it as heat, and I'm ready for the next cycle with very little energy investment, sort of to make up for the spring losses and the air resistance that my mass sort of sees. Now, there's an electrical equivalent to this. It's an LC tank. And the potential and kinetic energy interchange is precisely like that of the exchange between the electrical energy and the magnetic energy between the inductor and the capacitor. So with that, this in a slide is conceptually what resonant design is about. You've basically got the same driver and your load, but you hook up this parallel inductor to it. And this large capacitor here is to take care of basically of sort of steady state voltage issues and quiescent current. But let's ignore that for now. From an AC perspective, having this as a large capacitor results in an equivalent AC circuit that's an LC tank, right? Now, as you start driving this tank at frequencies close to the resonant frequency, you're basically able to get the same voltage transitions with very little current investment, right? Now, as you do that, you dissipate less. And obviously, at the end of the day, what we care about is dissipation to achieve a certain amount of voltage transition, right? It turns out that it's easy to show that the power dissipation of this system is intimately tied to its system Q, or system quality factor. So it can be shown that that expression is pi by 4q CV squared. The reason why I'm sort of putting this down is that the key takeaway from this slide is that this q is in the denominator, which sort of jives with intuition. You have a really high q. If you have very low losses, you have a very high q. That means you dissipate very little. And and on the opposite side, if you've got lots of dissipation, your q suffers, and you've got higher dissipation. Now, the early approach to exploiting resonant design was so-called adiabatic logic. The idea there is, let's take every single node in my entire digital system, hook it up to that parallel LC tank, right? Now let that sort of float up and down. And that's precisely what was done. You basically had this evaluation logic itself hooked up to the LC tank that would, depending on the logic outcome, connect the capacitive load or its complement to the resonant LC system. So for example, in the first cycle, you sort of wanted your logic evaluated true. This PFET device would sort of turn on, steer all the current to the true rail, and it would follow the clock. Now this clock was called the power clock because now not only does it do the job of synchronizing, it does the job of charging and discharging every single node. hence the notion of a power clock. Now, it tracks the power clock, and in the next cycle, if it evaluates false, the evaluation logic sort of steers current the other way, and that charges the complement rail. It goes all the way up and down, and that's how you affect computation. Now, note the key thing to note here is that the gates are inherently dynamic in that they work as directed by a power clock, a clock in this case, and also that the logic is dual rail, so that you are able to offer a consistent capacitance to the resonant system every cycle, regardless of what your computation is. So this idea of sort of resonating, using resonance to perform computation was very attractive to a number of researchers, and there was a lot of good work done in adiabatic logic. First was Eunice and Knight, who built the first split-level charge recovery logic, followed by Athis and Kim, who sort of demonstrated more substantial designs on chip. But these frequencies that were implemented stuck at around 100, 150 megahertz. It never really crossed beyond. Now, it is true that there's a fundamental trade-off between speed and energy efficiency when it comes to adiabatic systems. But the incorrect consensus that was drawn from this was that adiabatic logic had somehow reached its performance limits. And it was going to be stuck at around 100 to 150 megahertz for a given class of process. It was subsequently shown that these frequencies were not so much due to any fundamental efficiency trade-off, but more due to just design deficiencies. And that was proven by the work done on Boost Logic and Boost Logic 2 that sort of demonstrated gigahertz class operation for these adiabatic circuits. So for that technology at a gigahertz class, I was pretty much close to these fundamental limits. That said, however, recall that I'd mentioned that adiabatic logic is inherently dynamic in nature. It has a switching activity of 2. You'll also recall that I mentioned that the power dissipation expression was S CV square F. S was the probability that your node would switch. Typical microprocessor circuits, S is 0.1 or 0.15. Compare that to 2. What that immediately means is you basically need to have at least a Q of 10 to sort of break even. Your system Q needs to be more than 10 before you can start showing energy efficiencies over state-of-the-art CMOS. And for this reason, implementing or demonstrating energy efficiencies using adiabatic circuit techniques, I believe we'll have to wait for like a technology that's able to afford these kind of system Qs. So what do we do now? We either drop adiabatic logic altogether, and then lots of people who are working on their PhDs will have to find the next problem. Or we take the sensible approach and we say, all right, fine, but the idea is good. What can I use it for, right? What other net has a switching activity of 2, which also happens to be very dissipative and what everybody cares about? The clock. So now, instead of trying to resonate every single node in your circuit, you just try to resonate the clock. And that's precisely what some of the breakaway work from the main adiabatic logic community sort of involved. Chan and Drake, they proposed resonant clock distributions that drove traditional flip-flop banks. And while this, I think, is a step in the right direction, there were lots of challenges, unfortunately, I felt that this approach doesn't address. So for example, you've got the problem of process-dependent skew. So let's take a look at this conventional waveform and a resonant waveform here. And this conventional flip-flop, which was the proposed application. You drive this sinusoid into this clock pin for the flop. It goes through this inverter. Process variation on this inverter is going to cause a switching threshold uncertainty when, loosely speaking, that inverter sort of triggers. That uncertainty translates to a timing uncertainty or process-dependent skew. If you have a sharp clock, like conventional clocks, that's not such a big deal. But if you've got a sinusoidal clock, now we're talking serious performance hits. Another issue was crowbar current. having a sinusoid means you've got significant rise in fall times. For that duration, both the NMOS and the PMOS device here are conducting, and you're dissipating crowbar current. And third, and perhaps most importantly, I achieve resonance on the input of this capacitance. Great. It's going to trigger an output transition, and all that capacitance that's sitting behind it, that's probably 10 times higher, I can do nothing about it. It'll have to switch conventionally. So that's a huge opportunity lost there. For this and some other reasons, there was still no real silicon demonstration of data paths or real systems that were implemented using resonant clocks. Demonstrations were sort of restricted to either purely a clock tree or a clock tree driving a bank of flip-flops, but no real performance constraints, energy efficiency constraints there. One of my projects in grad school was to look at implementing resonant clock pipelines, and that resulted in the RCL, or resonant clock latch-based design methodology. That resulted, in turn, in the RF2 test chip, whose die shot is sort of shown here, and whose die shot is here, and a cartoon drawing of its clock mesh is shown here. So what RF2 is you've basically got this L implemented off on the side. It's amazing how much you can cheat in grad school. You got this inductor off on the side, and then you've got this data path here. The inductor sort of feeds into this global clock tree that then drives a mesh shown here. And on this mesh are where all your latches are hooked up to, right? RF2 was an 8-bit 14-tap FIR filter. And as I mentioned, the RCL design methodology allowed for a fully ASIC design implementation of a resonant clock system. So you'd go all the way from Verilog to place and route, and you would have a resonant clock system right there. Using the latch-based design ensured me that skew tolerance that sort of saved me from the process-dependent skew that I referred to in the earlier slide. So once you have a latch, the time borrowing that you enjoy sort of buys you some slack there. Also, a modified Swenson latch implementation solved the problem of crowbar current and ensured that the entire clocked capacitance of the latch was part of this resonant network. And this enabled 84% clock power reduction compared to CV square of the equivalent capacitance. Now, one pretty interesting thing about this distribution is that I was able to have these mini clock generators that were embedded within the latches. So as you place the latch and you connect that up to the clock, these cross-coupled devices end up repowering the clock right there. So just as you've got your loads sprinkled all over your distribution, you've got your drivers sprinkled all across. And that really enables you to do this very automated design for a resonant clock system. So all that resulted in, now we've got resonant clock pipelines that truly demonstrate energy efficiency for test prototypes that were published, right? Still, there was consensus in the design community that this was not really a plausible approach for a production, high-performance, high-volume design. One of the reasons was right here. Imagine you have a high-performance, high-volume processor. You care about how many square millimeters your area is, right? And then I come along to you and say, hey, I can really cut down a lot of your power. You just have to double your area. Not going to sell. In fact, it didn't sell. So this and other reasons were what led to a lot of people believing it sort of run its course, can't really push further. But it was ultimately done, and it was implemented in a high-volume x86 processor. Before I go into that, I'd quickly like to motivate that by looking at a global clock distribution for a high-performance, high-volume microprocessor, right? So you've got typically a PLL that connects to the root, drives, you have like an H-tree type system that distributes this clock to all spans of your design. And now this clock network, in turn, drives a global clock mesh that allows you to have a very low skew clock surface. This mesh then in turn drives clock gators, which are basically just glorified AND gates. And all they do is all this downstream clock distribution is gated off conditionally depending on whether this downstream logic needs to be clocked or not. Now you go from a switching activity of 2 for your global clock down to typically 0.1 to 0.25 depending on what you're running. In spite of this, the sheer amount of capacitance in your global distribution, along with the extent and the span that this design has, results in clock power accounting for roughly a quarter of high performance power dissipation. Now that's a huge amount. And many of you might be wondering, well, OK, if that's the case and my grid is eating up so much power, well, why don't I just lose the grid? Or equivalently, take some of these gates and move them further upstream so I can conditionally clock more of the downstream stuff, right? And those are perfectly valid things, and those are exactly what's done in medium and lower performance or other lower power type designs. It's not going to be possible for high performance, high volume designs to do this because notice the downstream distribution here, you can't connect these two up. Well, obviously, because they are conditionally clocked, or they're qualified clocks, may not agree with each other in polarity, you obviously can't short them. That basically means once you move these gators higher up, you can't have the grid. Once you lose the grid, either because you want to save power or because you want to clock gate earlier, now you don't get that low skew surface. And what that low skew surface hurts you, it hurts you two ways. You see a degradation in performance because it takes away from your cycle time. And now you've got increasingly higher risk of race conditions in your design, which is also manageable. But if you've got a huge high volume design, every part that you lose to race conditions is cause for worry. So the early work in this was actually done by IBM, and they did a very interesting clocking experiment on a customized processor. They basically took the processor as is, added to a layer of really thick metal, and the super thick metal was what they used to sort of craft their inductor. Was what they used to craft their inductor in parallel, as I described, getting that resonant system. However, there were some key challenges. You can't have a super thick metal in a production design. It just costs too much, and there are all sorts of yield issues that are going to come up. Frequency scaling is another problem. You are going to do great at frequencies close to the resonant frequency, but microprocessors, remember I talked about that wide power dissipation range from 200 milliwatts all the way up to 2 watts? Well, the way you get that is by running at different voltages and different frequencies, almost factor of 10, or at least for test, you need to support that wide range. You can't do that. Not only do you end up being more dissipative, but at the lower frequencies, your clock starts to warp, and you've got functional problems with even getting this to work. And that was actually an issue that they had to deal with and addressed in their test. The last problem is efficiency. You've got this low resistance winding, and it's given you high system Q on your inductor, but now you've built up eddy currents inside your power grid everywhere else. And those eddy currents are current flow in those power grids basically end up offering these mutual inductance terms that are very detrimental to system Q. With that, we come to the Piledriver global clock distribution. So a quick walkthrough of this distribution. It's a lot like that high performance design I talked about earlier. It's just geometrically going to be different, so I'll quickly walk through it. Your PLL clock sort of starts off at this root, gets spread along the height of this processor, and then across using these 5 bands, 5 horizontal clock tree macros, to 270 drivers that are peppered throughout this design, entirely within these clock macros. Right? Now, these drivers, in turn, drive a global clock grid. Now, this grid has to meet a very aggressive 7 picosecond skew target across its entire 21 square millimeter area. And a whole time driven methodology constraint limits the amount of staging you can do from this grid. And that basically means you're constrained to basically having just timing elements there. So you can't have too much delay between the grid all the way to the timing element. That precludes sort of staging, how much clock gating you can do. And for these reasons, about 24% of the average application power in the core went just in the global clock distribution. I'm not even including the part that was downstream after the clock gators. So we looked at resonant clocking with this design and implemented it that way. Inside, from a physical perspective, the resonant clock implementation involved taking 92 inductors and sort of distributing them within each of these clock macros, right? Now, each of these inductors and sort of associated circuit elements to make the whole thing work were confined to these clock macros so as not to disturb the remainder of the design process with your logic, your memories, your pipelines. So zooming into one of those 92 inductors, you've basically got a setup like this. Remember, you have to support a wide range of application frequencies, as well as a lot of lower frequencies for test. So for that reason, we implemented this using a dual mode clock system, where we have this mode switch that conditionally connects the inductor to the grid or disconnects it. So if you're in resonant clock or R clock mode, you close this switch, inductor is connected in parallel to your load, you're sort of resonating. If you're in conventional mode or C clock mode, you disconnect the switch, now you've got conventional drive. The schematic here is basically a modified clock driver that was done. You can see the split buffer implementation that helps control crowbar. And some of this other staging logic allowed me to do what I call a pulse mode drive, which is just an inherently much more efficient way of driving these kind of systems. This tank cap here, if you recall that early schematic which I showed you, have this huge capacitance, this AC ground capacitance here, connected in series with your inductor so that it is at the frequencies of oscillation, this looks like an AC ground. And having something about 6 times the clock load did the trick. That was good enough. And then there were some other details like the throttle switch, staging on the mode switch. They were taken to address voltage spike issues. Remember, you've got to have a processor that runs in resonant mode. Now, when you switch to conventional mode, it does it at runtime. So you've got to be able to do it on the fly. You don't get to power the thing off, sort of reprogram and continue. Everything happens on the fly at runtime. So once you do that, you sort of need to address issues with voltage transients. The one thing I'll sort of highlight on with this design, there was plenty of details, a lot of engineering work. A lot of it was done by the Piledriver design team. So I'm just going to focus on sort of the newer resonant clock aspects of it. The inductor design was substantially constrained. Some of you might not even recognize this as an inductor, especially if you work in analog or RF. The constraints really came up. They were both physical and electrical. Physically, you're sort of jammed in because your inductor needs to be inside the clock macro and within these power stripes that connect to the C4 bumps. Electrically, design management basically said, you can build your inductor, but you will get no extra metal tracks and no extra metal layers. Do what you can. So now you basically got to figure out, how am I going to build this inductor with the existing metal that's there and sort of snaking around what exists. So what was done was basically the design of this inductor, we basically implemented cutaways on the top level metal and like these tunnels here on the penultimate metal to enable your power stripes to run right down the middle of your inductor and your horizontal clock distribution to essentially run right through this inductor. And now care was taken to make sure that these power straps run strictly through the middle, because that allows you to get maximal mutual inductance cancellation, and that way you have the least detrimental impact on your inductor. Now we have the other question of the eddy currents in the grid. You'll recall that current flow in this inductor will cause eddy current flow in the power grid, sort of highlighted in blue underneath. And this eddy current sort of reflects back onto your primary side, decreases the impedance, now you've got loss. What was done to address this was basically the design of a custom loopless power grid that ensured that there were no loops that were formed in the grid, and at the same time, it was robust enough to drive the electronics that was actually there. The AC ground capacitance that was 6 times the load was also crammed into this yellow outline shown here to keep this as an entirely modular design. So I will just quickly gloss through some of this stuff. Now you've got your inductors. You can't build too many of them. Mind you, you've got a huge variety of clock load and clock skew concerns throughout this processor. You've got 270 drivers and 92 inductors, but the sheer complexity of the inductor design limits you to 5 inductors. You need typically about 35 different types of drivers to drive your loads, such as the variance across this chip. And you've got to do it only with 5 types of inductors. That made clock network optimization essential. And we basically developed a flow for that as well. I won't go into the details here, but we basically just did some of the early work, threw the stuff off to MATLAB, and MATLAB solved the linear programming problem, and then we sort of iterate. Because obviously, if you're going to do a linear program, you're linearizing a nonlinear problem. And even though it's not sort of strictly the accurate way to do it, it gets the job done, and you get a significant amount of skew control. So we were able to, with only 5 inductors across the chip, we were able to first meet our R-clock skew budget, and that ended up being only about 0.7 picoseconds higher than the conventional clock. Now looking ahead, I'd just like to share some challenges and opportunities that exist for energy efficient design. It's probably a good idea to sort of discuss the problem of power supply and power supply distribution to your chip. Now, the basic problem of power supply noise comes about because in spite of all the resources on the package that you devote to get your power and ground from the regulator to connect up to your power and ground on the chip, that impedance is still high enough for the current that you're drawing. And that results in supply noise. So shown here on the right is sort of an AC excitation response. On the x-axis, obviously, your frequency. And for a given frequency of current, it's showing you the impedance plot looking out from the die into the system. You've got your so-called first droop, which is very significant, roughly in the 100 to 300 megahertz range. Second droop in the 5 megahertz region. And then by the time you're talking about a third droop, you're in the kilohertz range. The first droop occurs because at the frequencies associated here, your cap is essentially a short. It's on the package. But looking in just from your on-package cap to your die, that inductance is enough to cause this huge increase in impedance. Likewise, your second droop resonance pretty much occurs due to LC effects that occur between your package capacitance and your socket inductance. So there's a lot of worst-case droop margining that's done. Sorry, a lot of worst-case droop margining that's done. So just look at this example, the simulation of a real load operating on a realistic package hookup for a chip with realistic parasitics. A stepped load causes your high frequency ring, which is your first droop, and your lower frequency ring, which is your second droop. And that droop costs about 200 millivolts, right? That's a good 15 or 16% of your supply budget itself. Now, all of that you're having to just waste because you don't know how to address the problem of supply noise. And there are various charge injection techniques that have been attempted in the past where they try to just inject charge into the supply. But doing so ends up being expensive and slower, and that sort of affects your efficiency as well. So the alternative approach to this, which was proposed, is why don't we just stretch the clock? The whole system is a synchronous one. The problem really isn't your supply noise, it's that you'll fail timing when there is supply noise. So clock stretching is a great direction, but we can still do better. What if we were able to speculate on droop occurrences? So your digital system is able to speculate on whether a droop will occur and stretch in response to that. And it might even be more elegant and efficient if we were able to use all this functionality within the clock generation system itself, using all digital PLLs, for example. Integrated voltage regulation is another interesting area. Having these on-chip voltage regulators provides much more enhanced voltage scaling. That way you can more effectively realize your CV square energy savings, both temporally and spatially. So we've got this plot here from Mong-Yong Kim. You've got this processor over time that has different processing requirements. And once you have an on-chip voltage regulator, you're really able to get into these nooks and crannies and really scale your voltage down much closer to what your needs are and save energy that way. Spatially, you're able to do those multiple voltage islands I talked about, provided you can design efficient on-chip regulators. And you can do that without those supply noise issues that I discussed. I'll sort of move along here quickly in the interest of time. But even IVR systems have some very interesting problems that they pose. One is line-side supply noise. These things might be able to regulate the voltage on the supply side, but on the line side, they're sort of pounding the power supply with very noisy current. And you're going to see supply noise there, and you're going to see oxide stress. You've still got the problem of cascading converters. Your input comes in at 12 volts, 20 volts. You can't put that directly on the chip. So you've got one converter that feeds the next converter, and you have to multiply their efficiencies. By the time you come off on the right, you're not saving that much. Next generation clocking is another effective area. I'll just sort of touch up on one area that's interesting, particularly in resonant clocking. And that's the idea of frequency scalable resonant clocks. We've all talked about how resonant clocking sort of sticks you to a given frequency, and you don't have that much scalability in terms of how you're able to move. One way to address that is what we did in Piledriver, sort of have a switch that moves in conventional mode at a given frequency and resonant in the rest. Or you could sort of have these tunable capacitors or switchable inductors, and that becomes lossy. So you end up dissipating, and you can't really move a really wide range. I believe if we rethink frequency tuning altogether for resonant clocks, it is possible to get an order, 2 orders of magnitude of frequency scalability by essentially just control circuits that will work at runtime and enable this kind of a stretching with the appropriate interaction of whole circuits. So that's sort of a view of how we are going to get this frequency tuning going. Other areas are on energy efficient gridless clock networks. I won't discuss this at length, but the basic problem is you've designed a you want to design an energy efficient clock. You don't want the grid because it dissipates too much. And oh, it's low power, so you want to scale the voltage down too. And when you do that, you've got huge amounts of variation. So it's almost as if designing an energy efficient clock is the same thing as designing a really high skew clock, which is obviously not what you want. And I think it's possible to come up with elastic skew architectures, elastic clock architectures that are able to manage this kind of clock skew that you end up having on the flip-flops and tuning them at runtime so you can optimize performance and not have that clock grid in place. Last area is interconnect design. Also a very exciting area. I love this slide by Bill Daly. It really succinctly poses the problem that we all face in the future, which is your 64-bit double precision floating point computation is 20 picojoules. Sending data across on buses within the chip is dwarfing that dissipation. So you've got the problem where sending the data is more expensive than computing your data. Now, that sort of opens up ideas on what can we do in terms of VLSI compression. Well, if processing is cheaper, particularly for low power systems and ultra low power designs, if processing is cheap, what can I do to compress? What can I do to pre-process and reduce the amount of work I have to do in transmitting this data. And that sort of naturally leads into the problem of network on chip design. On the whole, though, I guess in conclusion, I'd just share this view of what I think we'd ultimately want energy efficient systems of tomorrow to look like. You basically have this very heterogeneous set of computational units, all controlled by an online optimizer. This optimizer could be connected, for example, with a network on chip itself. It'll have a DSP system. The system could have memory, cores. Now, this optimizer will continuously monitor key metrics of all these accelerators, such as their temperature, their power dissipation, how you're going in terms of completion, thermal issues, as well as traffic that's on the network. And it would continuously run this optimization, feed back information to these cores, and say, here's what you need to do for overall optimal system performance. Configure architectural knobs in the cores and data path parameters, for example. Just power supply assignments, gating, as well as precision and implementation settings for the accelerators, memory partition and organization, and even network structure and arbitration rules to make sure that the system as a whole is operating in an optimal sense. In conclusion, we still have that problem. We need 10x improvement every 5 years. And energy dissipation is the foremost limiter to that enhanced performance. Sustaining that performance is going to need advances, obviously. And there is still no single silver bullet to the problem. We had it for 20 years. The process guys gave it to us. Now that's gone. And there is no single silver bullet. So what do? We just keep searching for one. And in the meantime, we start building towards an infrastructure that's able to efficiently incorporate a lot of the energy efficient designs in a manner that respects and considers all the complex relations and constraints that occur between them. With that, thank you very much. Any questions?
We have time for one quick question, if anyone in the audience has one, and the speaker will be available after the talk as well. I do want to announce that he's also looking for motivated graduate students. So if anyone is excited by the talk, please contact him as well. Any quick question before we adjourn? OK, so I have one for you, which is, what is the final limit in terms of computation, in terms of physics limit on the computation? How far away are we from that?
We are very far away from that. There's been some very interesting work on sort of information theoretic bounds on computation. There's a very good set of lectures by Feynman on that. KT ln 2 is sort of the number that's bandied about. But that number is very low. I think to get there, we have a long way to go. And there's a lot of energy savings that can be achieved still.
All right, thank you. And he's available down here as well. So another round of applause for Visvesh.
For all these